Hi everyone, welcome to week 2. So we're gonna jump right into it. So last week we kind of learned quite a lot of number of things. So we talked about vector spaces, these bases, linear independence, spanning, and all these kind of nice little things. But what we're gonna start off with today is we're gonna look at a particularly nice basis and how to kind of replicate this in a more general setting. And what this is going to be is it's going to be called orthonormal bases, which is basically what this what this next chapter is on. So basically, like if we remember like what happened in like school era, a lot of times when we're talking about like R2, so if we're talking about like the real numbers or the real plane, the way we normally do this is we'll draw like the x-axis, right? So we'll have a little x-axis this way and a little y-axis this way, right? So this is normally the bases that we had been seeing, I guess E1, E2, which normally we'd call X and Y, for example. This is our normal kind of setting that we've done like for millennia. I guess I should put this under to show that it's not E1 of X. There we go. And there's something special about this, and that's that these two vectors that we chose specifically are orthogonal to one another, right? So they're perpendicular because we're talking about real, like a Euclidean vector space. Nothing stopped us from choosing two vectors like this, right? So if I were to choose two different vectors like this, I can get any vector out there. It doesn't really matter. It just somehow doesn't feel as nice, right? So if they're orthogonal to each other, it somehow feels nicer. And this orthogonality, this like perpendicularity, is exactly what we're going to kind of look at. So what makes this special? What makes this basis special is the first one is kind of like the thing I was saying, that the basis vectors are orthogonal to one another. So the first property is that the basis, I guess basis vectors are orthogonal to one another. One to one another. And another thing that we kind of say is that each of the basis vectors, if you kind of notice here, I just drew them once, right? I didn't say it's 2e or 5e. I kind of like normalize them to be some set length. So we're also going to assume one nice thing about them is that the basis vectors are all unit length. Vectors are unit length. Here the reason why we're saying unit instead of length 1 is because we don't really know what, like if we're talking about arbitrary vector spaces, we're not necessarily going to be over R, right? We might be over some other field. And so it's worthwhile to not force it to be 1 if we don't need to. Okay, so these are the two properties we're going to need. And those two properties are precisely the idea we have with an orthonormal basis. So an orthonormal basis is going to have basically this definition. So we're going to start off with some set of basis. So some basis. So here, notice how this is an ordered basis. Remember that we can order our bases or kind of leave them as is. Here we're ordering them. It's going to be n-dimensional, so the basis has n vectors in it. Remember that gives us the number of elements in the basis, gives us the dimension of the vector space. So this is an n-dimensional vector space, and we're going to have this property that the inner product, so remember that the inner product is this kind of nice formula that has linearity and a few other properties, right? So it has symmetry, linearity, and positive definiteness. So it's going to have this property where whenever I take any two bases, the two basis vectors, and I take their inner product, then I'm going to be getting what's called the Kronecker delta. So the Kronecker delta is basically saying if I is equal to j, then we get 1. And if I is not equal to the j, then we set it to 0. So it's either 1 or 0. So if the inner product with itself is equal to 1, that means the length is 1. So that is, this 1 is saying unit length if for all I. And this 0 is basically saying orthogonality. And if we have these two properties, then we say that this basis is an orthonormal basis of V. So this is precisely kind of what we want for this to happen. Oh, I think I screwed up. Yeah, I read this wrong. So one thing to note is I had stated that these that we have an ordered basis here. Sorry, I jumped the gun. But actually, we don't even require it to be a basis. It just needs to be a set of vectors. So any set of vectors, and we're kind of good to go. And that's what the remark here I had right afterward was basically saying that we don't actually require it to be a basis. It can just be some set of vectors. Because you can actually check that using this definition, using this inner product, you can actually show that these vectors are in fact a basis. So yeah, so we don't actually need them to start off being a basis. They just need to be some set that satisfies these properties, and we're good to go. So it's kind of nice in that regards. So the kind of easy example for this, I think the fairly standard example of an orthonormal basis is just normal Euclidean vector space with just a normal canonical basis. So E1 to En, this is the kind of graph that we were talking about earlier, and the canonical inner product. So remember, this is just the dot product. So it's very easy and quick to check that that this formula here, that 1.8, is satisfied. So I'll leave that as an exercise for you to do. But so this, it's easy to here. Actually, do I have green? Yeah. It's easy to show that this satisfies this. So you can kind of check this out if you want. And there's like a little bit of a hint on the left-hand side if you do need a little bit of guidance on how to kind of do that. Okay, so we saw like we gave an explanation as to why we wanted orthonormal bases. But what properties do orthonormal bases have? Why are they actually nice? Why do we use them, right? Like, yeah, it's nice to look at, but what's the point? What is it there for? And that's because it basically lets us use the inner product in a nice kind of way. So it basically reduces the inner product on the space to the canonical inner product. So basically, no matter what inner product we looked at, it all goes directly to just the canonical inner product, which makes it nice, right? So because that formula we already know it's a dot product, nice and easy to do. So we have less things to kind of worry about. So to kind of see this, here on the top left, I have the inner product. So this is the inner product, some arbitrary inner product. We don't know what this is. And here, if you kind of see, this is what we would normally think of as the dot product, or the canonical inner product. So let's actually show that these two are the same. Let's see how this kind of works. Well, first we have that x, right? We can decompose it as, since A1 to En is a basis, it's an orthonormal basis, we can decompose x and y as basis vectors. So this we can decompose yj, ej, all the way to n, I is equal to 1 to n. Okay. Here we're going to use the linearity property of orthonormal bases, and also of inner product, and also the symmetry property. And we can basically take out all of these exponents or coefficients and bring them to the front. So basically we have the double summation. We have I equals 1 to n, j equals 1 to n, xi, xj, ei, ej. Yeah. But here, if you think about this, this is just the conical delta. So here, this is I equals 1 to n, j equals 1 to n. of xi xj, Kronecker delta of ij, right? And here, what happens? So this, if we kind of recall, right, this is equal to 1 if I is equal to j, 0 otherwise, right? So if because of this double summation, whenever the two are different, then it just disappears. So in other words, we can merge this summation into one over one variable, and we just have to keep this product, and that gives us precisely this dot product. So that's what makes this nice. It really allows us to kind of see exactly what's happening. It allows us to use an easy product to kind of do this. Another nice thing about these orthonormal bases is that actually every finite dimensional Euclidean vector space, so here I'm going to highlight finite dimensional because here we're using that as finite dimensional. Every finite dimensional Euclidean vector space has an orthonormal basis. So these things do exist. So no matter what dimension we're in, we're always going to have this. So as a result, because every single vector space has this finite dimensional, and this is what we're kind of going to be doing it, we're going to basically stick with this, right? So we're going to let, what we're going to do is we're going to let En, so here En, we're going to denote this as the n-dimensional Euclidean vector space with an orthonormal basis. So here the emphasis is with an orthonormal basis. So it's all of this together. So in other words, whenever we're talking about this, the inner product is always just going to be the canonical inner product and stuff like that. So we'll stop here for this lecture, and we'll come back in the next talk or in the next lecture video thingy, and we'll see what happens when we look at matrices and how this kind of works with an orthonormal perspective. So I'll see you then. Peace.